we're going to basically continue on with move on with our discussion of kind of mechanics. So in lecture 10, you all are experts now in kind of mechanics and dealing with these stress strain curves, as we've kind of talked about previously. So your yield stress, all that good stuff. We also related the our stress tensors to basically our strain tensors as well. Actually, let's do our most general form of anisotropic linear elasticity. So sigma ij equals sigma cij kl epsilon kl. So second rank tensor, first rank tensor, all that good stuff. We know how to rotate our stress states in Mohr circle and everything else. But in lecture 11, we're going to kind of talk about, okay, we know we could generate a stress strain curve using an extensometer, which we've talked about right here, in order to measure strain, which is, again, most simply, your engineering strain is the change in length over some initial length L naught. But now we're going to see, can we measure really complex stress states? For example, if we have a thin wall pressure vessel and there's some type of defect or crack around here, we can place a strain gauge on or near this section because we know that that crack will concentrate our stresses, so it won't basically follow the laws of linear elasticity, and we can kind of measure the strain near those defects and figure out what is our kind of stress tensors as well. So in lecture 11, we are going to talk about strain gauges, circuits, specifically basically Wheatstone bridges. Wheatstone bridge circuits, and how to measure strain. So you can use an extensometer, which is, again, in your uniaxial tensile test, you basically stick a kind of this material that clips onto your thickness, so it'll clip onto here, and so as your material deforms, you will actually kind of measure this displacement over some initial gauge length. But you can also measure strain using some type of electrical strain gauge. So these can be resistive, inductive, or capacitive. So there's many different types of strain gauges. Some might be better for your application, but we are going to be talking primarily and almost exclusively about resistive strain gauges. So we're going to relate some type of displacement of our material, some strain, in order, we're going to convert strain to some change in resistance, and that is how we're going to kind of measure strain using our resistive strain gauge. Yep. So, and there's different other techniques too, optical properties, but those are a little bit less common nowadays. So, a brief history of kind of the electrical resistance strain gauges. So, is found or basically discovered by Lord Kelvin. And it's the same as basically the unit Kelvin. Okay. So he found that Lord Kelvin found that the resistance of copper and iron wire will change when the wires are subject to mechanical change. So basically, if you have some type of wire like this, zoomed in view, you pull it, you change essentially the length here, and what also happens, so there's going to be some strain axially, which is going to be some change in L over some L naught. There's also going to be some compression laterally, and that's going to be some change in your diameter, effectively this wire, change in diameter over diameter naught. We know that that lateral contraction is going to be related to our property Poisson's ratio, which is, remember, 0.2 for ceramics, 0.3 for metals, 0.4 for polymers or biomaterials. So Lord Kelvin also used a Wheatstone bridge in order to kind of a Wheatstone bridge circuit in order to kind of measure that change in resistance as a function of that change in length. So Carlson actually introduced the wire resistance strain gauge in 1931, and in 1938, Simmons made a bonded wire strain gauge covered by patent basically by Rouge, who was at MIT at the time. So when a length of the wire is mechanically stretched at a longer length, smaller cross-sectional conductor results. It changes the electrical resistance of your wire. So we can basically look at the length. If the length of the resistive element is attached to a strained material, the element is strained in the same manner. The change in resistance can be calibrated in terms of strain. So we are going to calibrate strain, and we're going to basically apply some displacement or some strain, and we're going to calibrate it based on some change in resistance. So that is going to be kind of the fundamental equation that we're going to be looking for here. So just like we kind of saw there, excuse me, let's go back one more page here. As we just saw in that example, that we kind of if we have some initial conductor, some wire of length L, cross section C, D is your diameter, C is just going to be some constant, that's a geometric constant, strained axially, in tension, it will increase the length, and that lateral direction will decrease due to Poisson's ratio. So we can actually calculate the change in resistance. So if we strain a material, if we increase that length, we can figure out what is the change in resistance. So your resistance is a function, is basically given right here. So R is your resistance. This row is your resistivity, and then the rest of the parameters we've already kind of discussed here. So we can figure out what is the change in resistance. The change in resistance, we're just going to basically do a chain rule. So some little bit of math here. So R with respect to resistivity plus del R, change in R with respect to L, plus dr with respect to D. And C we know is a constant. So again, as we change or as we stretch our material, our resistivity is going to change, our length is going to change, that diameter is going to change. So just do some partials here. We could do some mathematics as well. That is just going to be L over CD squared. My dr dl is going to be rho over CD squared, and dr dd is going to be minus 2 rho L over CD3. So plugging in a chain rule, you can kind of see in doing some rearranging, we'll eventually get this expression here. So that change in resistance related to kind of those other values. If we divide by R, a little more mathematical changes here, you'll get this expression. And if you rearrange and divide out by this parameter, you'll get this value here. Now, what is the change DL over L? That is essentially our axial strain, which we talked about previously, right? The change in length over the initial length L naught. That's the axial strain. As we pull our material, pull it like this, that is our axial strain. We also know that there's going to be some compression, or a compressive strain there. So the lateral contraction is going to be change in D over D naught, or near initial D, which is just given right here as well. And Poisson's ratio, we know Poisson's is minus E lateral over E axial. So that's also given right here. So we can rewrite and rearrange this expression. Gauge factor, we can kind of figure this out. Well, this is typically given in these problems, and typically is determined experimentally by a manufacturer and given as a constant. You can actually calculate out. This is an actual expression, but again, when you're working with strain gauges, typically the manufacturer will give you that gauge factor constant F. So more importantly, we can rewrite essentially these expressions, knowing kind of these values here and this change in resistance above, and we will find kind of one of the fundamental equations that we'll use in this section of the course. So it's an extremely important expression, and that is going to be that our strain is going to be 1 over F, the gauge factor, times the change in resistance over some initial distance R. So F and resistivity is going to be, or overall resistance is going to be determined by the manufacturer, and we're going to determine how much we change R by changing that material. So this is an extremely important expression. Remember this strain. Again, that was kind of the whole discussion. We're going to relate strains to some change in resistance overall. That's it. So there's a lot in this kind of lecture that we're going to kind of skip over, but it's nice to kind of read over. So if you're kind of working with strain gauges, here are some desirable properties when you're kind of trying to select strain gauge materials. So you can kind of read through this, again, especially if you're kind of working with strain gauges, especially for senior projects. But we're going to kind of highlight some of the big aspects that we're going to cover in this course. So we are going to deal with single element gauge for uniaxial stress, 2 element rosettes, for biaxial conditions, and 3 element stress conditions for completely unknown conditions. So we are going to use this, and we are actually going to draw, basically over 2, you're going to draw your Mohr circle for strain space. So you're going to have kind of these 3 different values, and we're going to draw a Mohr circle because it's going to conduct through this. So more on that quite a bit later. But again, this is our fundamental expression. We're going to work with this quite a bit. So circuitry. We need to figure out, again, to measure change in resistance, we can't really just use an ordinary ohm meter. We're going to have to figure out, we need much higher precision in order to, because we're measuring strain in micro strain. typically. So we need to kind of basically figure out the change of resistance by a change in voltage. So we are going to start off with this voltage divider circuit and build up into our Wheatstone bridge, which you're going to see is going to basically be 2 voltage divider circuits. I have to give it away. So let's look at this expression. I don't like to use E, so I'm just going to use V naught. Let me use VI. So let's say that V naught is approximately 0, that there's basically negligible current being drawn from here. So you can kind of almost think of that as that V naught is unconnected, or we're not drawing anything from this. So what is going to be the current I in our system? Well, hopefully we all remember Ohm's law. So V equals IR. So are we connected in series or parallel here? So what is our equivalent resistance? We're in series, so it's just R1 plus R2. So my current is just going to be what? I'm going to rearrange VI over R1 plus R2, just as you can see here. So that's it. That is the voltage divider circuit. Again, if we're drawing some negligible current there. So what happens if there's a non-negligible amount of current flowing through V naught there? How are we going to kind of figure out what is the relationship with V naught? Well, V naught is just going to be what? It is going to be, if the V naught is non-negligible, so if it's not approximately 0, V naught is just I times R2, right? That's just our expression from Ohm's law. So we can plug in, we know what I is. So as you'll see on the next page here, if we plug in this expression where I is equal to here, we will find on the next page that the output voltage, your V naught, is just going to be this. R2 over R1 plus R2 VI. That's it. So that's your voltage. We're going to build up here. We're going to get to the Wheatstone bridge. That's going to be kind of the main thing we're working with. But the voltage divider circuit's a nice starting point because, as you'll see, this is what we're working towards, the Wheatstone bridge circuit. And you'll see what we call a standard configuration here. So we're going to name this arm, and we'll see it typically shown this way from here on out. This is actually a little bit different. So 1, 2, 3, 4 is going to be kind of our standard Wheatstone bridge configuration. But we'll get more on that in just a bit there. So Wheatstone bridge, do you kind of notice something here? These are basically, a Wheatstone bridge is basically just two voltage divider circuits. Voltage divider circuits. So we see here and here, and here and here. It's essentially the same, essentially just 2 voltage divider circuits here. So what are our unknowns here? Typically, we're going to know what is R1, R3, R2, and R4. But we have kind of a lot of unknowns here. And again, I want to get rid of this. As your output voltage, this is your input, VI. We will typically know these values. But I1, I1, I2, I3, I4, and IG. So that's 1, 2, 3, 4. We will have basically 6 unknowns here. So these are all unknown. So I have 6 unknowns. How am I going to solve and figure out for those values? I'm going to need to write 6 equations. So I hope you all remember basically from your circuits class. So we have especially Kirchhoff's first law and Kirchhoff's second law. So Kirchhoff's first law, current entering a node must equal the current leaving the node. So I've got several nodes here, right? So let's start off with at A. At A, what's the current entering my node? It's just II. What's the current leaving my node? I1 plus I3. What about at, what's happening at C here? What's the current entering my node? Well, it is I2 plus I4. What is the current leaving my node? That is equal to II. What about at B? So at B, it's right here. So at B, the current entering is my I1. The current leaving is I2 and IG. What about at D? Let's scroll down just a little bit here. At D, current entering I3 plus IG equals, or in the current leaving, is I4. So that's it. So we already have 4 equations. Now, what about Kirchhoff's second law? Sum of voltages around a loop must be equal to 0. Again, V equals IR. So let's look at the first, at one loop. So let's look at, for example, let me scroll up here, and I'm going to erase a couple of these just to give us a little bit of room to work with. So some of the voltages around it must be 0. So let's look, for example, let's say at BAD. So BAD. So what is kind of the sum of the voltages here? Well, it's going to be, if I'm going to go around from here, here, here. So, and then there's going to be kind of closed here, this IG. So I'm going to go I1, R1 is equal to, or excuse me. So in that direction, actually, let me get the eraser. I1, R1 minus I3, R3. And then I'm going again in that same, or that direction, it's opposing there. So plus IG, RG equals 0. So when I'm going basically across, so I'm going against that I1 direction, I'm going with I3. IG is going in this direction, so I'm going, again, against that current. So that is my first expression for BAD. My bad circuit, my bad loop. What about BCD? So I'm going BCD. That is going to be equal to, again, I'm going with this, so minus I2, R2, plus I4, R4. And then where we're going against there, so plus IG, RG. And that's it. And that's equal to 0. Sum of the voltages, again, Kirchhoff's second law, Kirchhoff's first law. Now we have 6 equations we can solve for our 6 unknowns here. And that's it. So once you go and you can solve for that, and we know that basically at balance, the voltage across the meter should be 0. And once you plug in that relationship, basically the voltage across the meter, so V naught, or basically it should just be IGRG is equal to 0. That is basically what's going on here. Once you plug in that relationship, you'll find that I1 equals I2, I3 equals I4, and you'll have this relationship as well. So once you have that, then you figure out what's the voltage. The voltage is just the voltage at B here minus the voltage at D here, which again is your just two, this arm, let me erase here. Just get a little bit messy. So what is the voltage at B? So again, it's this arm and this arm versus the voltage at D, which is this arm and this arm. These are your voltage potential dividing circuits, right? So we saw just from right here, so you can imagine if you stretch out that arm, you'd get a circuit that looks like VI, and then cross here, and it'd be R1, and then this would be your R2, and then across from there would be your kind of the voltage out here, V naught, IG, et cetera, et cetera, et cetera. So if you look back a couple pages, or actually just this last page, this is the exact same setup that we are working with over here. So what is my voltage at B? It is just R2 over R1 plus. What is my voltage at D? It is going to be, again, that R4, looking over here, that R4 minus, R4 over R3 plus R4. So it's the exact same, these are just two voltage potential dividing circuits. And that's it. And you'll notice that when the bridge is balanced, i.e. V naught is 0, you'll find you recover that relationship that you see right here. So that's it. That's our Wheatstone bridge. So let's see how we can actually work with that. So we mentioned this kind of, again, we're going to be skipping a lot of kind of parts in this section. So if we don't cover it in class, you'll kind of see me kind of essentially cross out some of these sections. So if I'm not talking about it in the video, again, they're good to know and good to read about, but basically especially for exams or for problem sets, they're not super necessary exactly. So we've set up kind of this idea of the standard configuration. of our Wheatstone bridge. So standard configuration is very important. So 1, 2, 3, 4. That is going to be the standard configuration that we will set up quite often, or actually all the time, for our Wheatstone bridge calculations. So 1, 2, 3, 4. So these can be either resistors, or we'll see in a second, we will replace sometimes, we will replace these with strain gauges, where our strain gauge will always have kind of these wires, wire bonded, again, resistive strain gauges along that kind of long axis of your rectangle. So strain gauge bridge circuit. So we can use this Wheatstone bridge configuration, and we get this relationship that we just showed last time, that your output voltage is equal to this. At balance, your output voltage V naught is equal to 0. So this is the scenario here. So we are asked to consider, let's start off with a simple scenario where in our standard configuration, we have this idea that we have a resistance 1, 2, 3, 4. We have our standard resistors, and at balance, these resistors all must be the same value. So the resistance, so if I have a Wheatstone bridge configuration like this, and they're all resistors, 1, 2, 3, 4, I need to make sure my resistance of 1 is equal to my resistance of 2, is equal to my resistance of 3, equal to resistance of 4. You'll see that typically kind of happen there. So, but here, we have resistors everywhere except we have a strain gauge that's being pulled on in tension in the 2-arm of our Wheatstone bridge. So this is kind of like called the 2-arm of our Wheatstone bridge. So undergoing uniaxial tension. So we're going to have our initial resistance, R2, and it's going to change by some amount because we know we have this relationship. Again, super, super important expression, right? Remember this. We need to kind of almost have this memorized to ourselves at this point, which is 1 over F gauge factor change of resistance over some resistance R. We're going to correlate our strain with some change in resistance. So that is what's happening here. So there's going to be some initial output voltage times some change in output voltage due to that change in resistance, R2 here. If you divide out by R2, we're going to kind of simplify our equation a bit more. We'll see that on the next page. So just doing some math here, dividing by R2 gives us this, dividing by R3 gives us this value right here. Once we assume that R1 equals R2 for equal resistances, that's what we kind of said previously, we get this final expression here. This, again, is plugging in from our strain is equal to 1 over F, change in R over R. So once you plug that in, you flip that. So change in R over R. So change in R2 over R2 is equal to epsilon F. So that's what we plug in to get this value right here. So this is great because, again, we're seeing now we can not only correlate a change in resistance to strain, but now we can correlate a change in voltage over some initial voltage VI to a change our strain. This is what we're looking for because the voltage, this Wheatstone bridge can measure extremely, extremely, extremely small changes in strain we couldn't have used if we just used an ohm meter. So that was our whole kind of analysis and kind of work to get here. Additionally, you'll notice that this term, because again, we're dealing with strains that are going to be 100 times 10 to the minus 6 strain values. This term is going to be really, really small compared to 4. So you'll typically see that change in V naught is going to be equal to 4 B. So for this specific example. So you'll typically see not VI E. Excuse me. Let me erase there. VI times F over 4. That's it. We'll see how we're going to get this to from a more complex, actually a more thorough expression in a second. So this only holds for that this specific. Basically, one arm is our strain gauge. So 1, 2, 3, 4. This is also called a quarter bridge configuration. So only a quarter of our bridge has strain gauges on it. So we could have a configuration that's called a half bridge, where you have 2 strain gauges, or you could have a basically a full bridge, or half bridge or full bridge configuration, where every arm is a strain gauge. So that's it. One quick note here. This is the bridge constant, K. So A, we're going to see on the next page, A is going to be the bridge output. So this is going to be your actual bridge output, and then B is the output of, say, arm. If we just had a single strain gauge. So so this is going to be the output of R1. So this is going to be the total output. We're going to see what this is in a second. So we'll come back to basically bridge constants and how we calculate that in just a bit. So we are going to skip ahead and we're going to get back to a couple of these values in a second. But we want to get to kind of the real fundamental equation that we're going to use in order to kind of relate the change in voltage to kind of our resistance strain gauges. So we've just done this kind of derivation for, again, a quarter bridge configuration. Only this value, that R2 changing. But we're going to have, let's do it for the most general case. So what would happen to our voltage if all of our strain gauges were changing? So we, again, had this expression here. We're going to use that quite a bit. But what would happen if instead, what would happen to our change in voltage if we had a configuration like this? So 1, 2, 3, 4, where we had strain gauges everywhere. Excuse me for my horrible drawing. You should be used to that by now. What if the strain gauges were everywhere? I.e., what if there was a change in resistance of 1, 2, 3, and 4? How would the voltage change here? Well, again, you just do these kind of partials. You could do these partials in Mathematica. These are just kind of, again, check your math, make sure that you could kind of get this correct. But what we end up with, and again, assuming that we have that initial equal resistances, which you have to be at balance. So this is our requirement for balance here. But once you kind of rearrange and you substitute this in for this expression up here, you'll find this really, really, really nice expression that we're going to use for the remainder of this course, which is this. So your change in voltage, your change in output voltage is going to be over your initial, your excitation voltage. So this is your output versus your excitation. It's going to be gauge factor over 4 times the strain in your first strain gauge minus strain in the second strain gauge minus strain in the third plus strain in the fourth. That's it. That is going to be what's happening here. So let's look at a couple of examples and what's going on here. So what would happen, for example, let's say I had the following, so let's say I have a material like this, and uniaxial tensile test right here. So my material is like this. I have one strain gauge at the top, and it's being pulled here. So what are the total strain, assuming that I'm in pure tension, so no bending. So my Wheatstone bridge would look like this. So 1, 2, 3, 4. So I have a strain gauge here, and then what else is happening? Just resistor, resistor, resistor. So if I have resistors in 2, 3, and 4, I'm not pulling on those resistors, right? They're just stuck in my circuit. So those wires aren't being pulled on. They're not changing. So my E2 is equal to 0, my E3 is equal to 0, and my epsilon 4 is also equal to 0. What's the strain in 1? Well, it's just going to be that strain and tension. So, or basically if we have a coordinate system like this, so let's look at it here. This is 1 and 2. That's going to be my strain in 2, 2, plus what else? So temperature is important, right? So if I'm looking at the strain in 1, it is also going to be doing what? It is going to be expanding in temperature. So we always have to kind of add this temperature component here. So your material or your strain gauge will be basically slightly thermal expansion coefficient. It's going to make it want to expand here. And you'll assume kind of it's going to expand equally everywhere. So we'll have to kind of encapsulate this temperature right here. But that's it. That's the strain in my one strain gauge. And that's it. So again, if our wires are going in this direction, that will be our kind of value here. Now what happens if we're elongating that strain gauge? We're going to say that it is, again, if we're elongating our wires, that is going to be positive. If we're compressing our wires, that is going to be a negative value. So we're going to have to work with that in just a second. So let's say instead, what if we had, for example, let's look at a new page. what if I had the following scenario? So what if I had a material like this? So here's my material. I'm pulling in this direction, and I'm also pulling in this direction. So biaxial stress state. That is going to get a little bit more complicated, right? So what is happening, and if I have a strain gauge like this, so here's my coordinate system. So I have 1, 2. So again, I'm going to say this is 1, 2, 3, 4. So what is happening to the wires here? So there's some stress 2, 2. There's some stress 1, 1. But everything else is 0. So my stress tensor is just going to be this. So sigma 1, 0, 0, 0, sigma 2, 2, 0, 0, 0, 0. So what is the strain in my one strain gauge? So there's a strain gauge here, and everything else is wires. So I know my change in voltage is just going to be naught times F over 4. The only thing left is E1. So what is my stress in 1? Well, it is going to be basically the strain in the 1, 1 direction. So my strain measured in the 1 is going to be this, 1, 1 positive minus nu E, or excuse me, in the 2, 2 direction, minus E 1, 1, right? Why is it minus that strain there? Because again, it's all about where the wires are moving. So the wires here, it's elongating in this direction. It's elongating in the 2, 2 direction. But as I'm pulling here, my strain gauge is going to shorten, right? And it's going to shorten by that Poisson's ratio there. So that is going to be kind of the change in strain in that scenario. So we'll get more into this and do lots more examples. Look forward to that to come. And we'll calculate bridge factors and kind of do lots of other kind of values as well. So we'll talk more about that. We'll do some examples. And yeah, I'll see you all next time. Thanks.